Hi everyone. Today we are going to start our discussion on section 4.6, which looks at the quantum mechanics as well as bonding hybridization. So this is going to delve into looking at the theory that helps to our understanding of how atoms come together to form molecules. We're going to cover this section over the next 2 days due to its complexity and the importance of being able to understand what hybridization actually is with respect to bonding. All right, so we're going to get started. We know up until this point that quantum numbers are used to describe the location of the electrons in an atom. So it tells us the overall probability of where the electrons pairs are going to be found. We've also been introduced to the Lewis structures, and we use Lewis structures to help us in visualizing the bond formation between atoms within molecules. All right, so we can determine how many bonds there are and how many lone pairs are found about the central atom. So from here, we've been able to predict the molecular geometry of the molecule using the VSEPR theory. But neither the Lewis structures nor our VSEPR theories actually helps to describe how the bonds actually form between atoms within molecules, nor does it help explain how the orbitals actually interact to form these bonds. And so this introduces us now to the valence bond theory, which helps to explain how orbitals are involved in bond formation. This theory was developed by Linus Pauling, and so he uses the idea of describing the electrons that are found in the bonds, which is going to come from the valence orbitals, okay, the ones that are found in the outermost shell. These are the ones that are going to be involved in forming our covalent bonds. We call these our valence orbitals. And so according to this theory, a covalent bond occurs when two orbitals overlap each other. Each of them has an unpaired electron. And so when they combine together and overlap their orbitals, now both of the atoms have two electrons shared between them of opposite spin. The result of this covalent bond decreases the overall energy and gives it its lowest energy configuration. So that's the basic premise of the valence bond theory. So let's take a look at some examples of what his theory actually means using orbital diagrams. So the first examples that we're going to look at are some diatomic molecules, all right? And the first one we're going to look at is the hydrogen molecule, the simplest of the diatomic molecules. If we look at the orbital diagram for a hydrogen atom, it has one electron in the first s orbital, the 1s orbital. And so this here shows one hydrogen atom. So this is a hydrogen atom with one valence electron. And this one here is another hydrogen atom with one valence electron. Notice that the electron that is found in each of these is spinning an opposite spin. So one is spinning down and one is spinning up. As these two atoms approach each other, they're going to overlap. Their orbitals are going to overlap, as you can see in this diagram here. Okay, so they overlap, and this overlap is where the covalent bond is formed. And so this results in having these two electrons being shared between the two atoms. This is a lower energy state than if the atoms were individual atoms on their own. All right, so let's take a look at another example. So it's very easy for 2s orbitals to overlap. Another example of a diatomic molecule, hydrogen chloride, also has the ability to form covalent bonds. What's going to happen here is that we know already from the previous example that the hydrogen atom has a half-filled s orbital, one s orbital, and chlorine, if we look at its orbital diagram here, if we consider it, this is the orbital diagram of chlorine, of a chlorine atom. Okay, and we see here in the valence orbital that this one here has one electron in it. So this is a half-filled p orbital. Okay, and this half-filled p orbital is going to come into close proximity to a half-filled s orbital of hydrogen, and they're going to overlap to form that covalent bond. All right, so if we take a look here in the chlorine atom, this gives us an illustration of what actually is taking place here. Here's my half-filled s orbital. Okay, this is an s orbital of hydrogen. And here is my p orbital. So I'll draw the p orbital up here as well. So don't forget, this is what my p orbital looks, and there's an electron somewhere in this p orbital of chlorine, okay, which is its valence orbital. And that's what's shown here in this diagram. So here we've got the one electron in this p orbital. So this electron here can be found anywhere within these two lobes. All right, so as these two approach each other, they overlap. So there's the overlap that takes place. When they overlap, we form a covalent bond. And so now the two electrons take one going in counterclockwise, the other one going in clockwise. They have opposite spin once they have formed that covalent bond, okay, and having the sharing of the electrons. Okay, so this is very, very important to show how they form this covalent bond. Okay, so the two lobes are going to overlap and it forms our covalent bond. Now, we can also have the overlap. This is example number 3, where we can overlap two p orbitals, both of which must be half-filled. So if we think of the orbital diagram of fluorine, a fluorine is going to also have a half-filled p orbital. All right, so this is one fluorine atom. And this is another fluorine atom. It's p orbital with one electron. Okay, so both of them have one electron. They're half-filled. If we're to draw the energy level diagram or orbital diagram for a fluorine atom, one of the p orbitals would be half full. This is what this represents. So we have two atoms of fluorine. They come to close proximity to one another, and what happens is their p orbitals overlap. Okay, so this is what we're showing here. This is the overlap of the two p orbitals. So I've got one electron in one orbital, one electron in the other. Okay, and so what ends up forming then is a covalent bond. Okay, so this represents my covalent bond between the two fluorine atoms. Okay, so that represents the two electron pairs that are being shared between their atoms. So in essence, what's happening here is the orbitals, which are half full, so they can be s orbitals with two s orbitals. It could be an s and a p half-filled orbital, or it can be two p orbitals. As long as there's only one electron, we can have them overlap and form a covalent bond. Now, this can also occur with some larger molecules, such as ammonia. So let's consider the orbital diagram for nitrogen. Okay, so we look here for nitrogen. This represents the valence electrons. Okay, we're not drawing in this orbital diagram the valence orbitals. We're not going to include the 1s2 because don't forget that 1s2 is also filled. So we'll notice here in the valence orbitals, we have 3, this here represents 3 half-filled p orbitals. Okay, and we also have 3 hydrogen atoms with a half-filled s orbital. And so that's what we're going to see in our next picture. Okay, so we see here the 3 hydrogens. These are all s orbitals with 1 electron in each of them. And this diagram here shows the 3 p orbitals along the x, y, and z plane, each half filled. And so what happens is, one of the atoms, these two come to close proximity to one another, this one does, and this one does. And so it shows the overlap, all right? Each of these, there's an overlap here of where the covalent bond is formed. So there's an overlap here, an overlap here, and there is a bit of a typo in this diagram. The other overlap will happen right here, not here. Okay, so there is a typo there, and so please make sure that you correct that. Okay, and so let's actually fix this here and make sure that we have them going in opposite spin as well. All right, we've got going one opposite, one going up and one going down. All right, so there is a typo here, folks, so please make sure that you fix that. So there's a typo here. The s orbital of hydrogen should actually overlap right here. All right, so this should be your third overlap. And so finally, you're going to end up with 3 covalent bonds between nitrogen and the 3 hydrogen atoms. So this all sort of makes sense. We see in the diagram here that the bond angles look like they're 90 degree angles. Yet we know that Vesper tells us that the geometry of this ammonia molecule is trigonal planar, okay, with bond angles of 107, because they're going to be less than 120. So to account for this valence bond theory, we need to expand it and include the concept of what we call hybridization. All right, so we're going to introduce what hybridization is. So they had to develop the valence bond theory a little bit further to try to explain some of these exceptions and anomalies that they were seeing. All right, so we can now summarize what the valence bond theory says. All right, very important statements here. All right, this one is very, very important. That a half-filled orbital in one atom can overlap with another half-filled orbital of a second atom. And that is how we form a covalent bond. Okay, and this new bonding orbital where the overlap occurs contains a pair of electrons of opposite spin. So a maximum number of electrons in this new bonding orbital that's been formed is always going to be 2. Okay, and when the atoms bond, they want to arrange themselves in 3-dimensional space to achieve the maximum overlap of their half-filled orbitals. Okay, so this is going to produce the lowest possible energy. So a lot of very important points here that you need to make sure you understand. All right, what we're going to move on to now are called hybrid orbitals. And the reason this part of the theory had to be developed is because there were two problems. The first problem is that it wasn't able to explain the four equal bonds that are present in molecules like methane, CH4, okay, and which had a tetrahedral shape. So we'll take a look at explaining why this has to happen in order to be able to form four covalent bonds that we know that carbon does. The second problem was the existence of double and triple bonds. And hybridization and the formation of these hybrid orbitals helps to solve the second problem as well. So today we're going to focus just on problem one, and tomorrow we'll delve into problem number two. So let's take a look at the atoms that tend to be exceptions to the octet rule. All right, so one of the problems is nicely illustrated with beryllium. All right, so if we take a look at beryllium and we consider its orbital diagram, so let's just do a quick little diagram of its. It has 4 electrons, so if I draw 2 electrons in the 1s orbital, so this is a good little bit of review. In the next orbital, 2s, it has 2 electrons, which gives me 4. Okay, it gives me 4. And so now we've got the 2 p's, which are empty. So these here represent the valence orbitals. Now you'll notice that the 2s orbital is full. And so that concludes to us, if I've got a full orbital, it should not be able to bond with other atoms. It's full. But we know for a fact that beryllium actually does form bonds. So how do we explain the fact that beryllium is able to form 2 covalent bonds? How they're able to explain this is the fact that it is able to promote one of its electrons from the 2s orbital of the valence orbitals to an empty p orbital. All right, there's a promotion. It promotes one electron. And so when it does this, it hybridizes. Hybridize means to blend. It hybridizes an s orbital and a p orbital. Okay, so we call this an sp hybrid. And in each one of them, now, each of these orbitals are half full. Now don't forget, the other 2 orbitals are still there. Okay, those are my 2, we call them unhybridized p orbitals. All right, so they still exist. They're still there. So now this sp hybrid has the ability to bond with other atoms. And so this sp hybrid has a special shape. It is linear. All right, and so it is linear. So it has this shape. It looks like a p orbital, but it's not. All right, it actually has an electron in each lobe. So what's really, really important to understand that this lobe here is called an sp hybrid, and this lobe here is also called an sp hybrid orbital. All right, and each one, it has 1 electron. The shape of this is linear, so that's very important to know, and it's 180 degrees. Okay, and so this sort of ties in our VSEPR theory. So now this beryllium sp hybrid when it comes into close proximity to two hydrogen atoms, they will overlap. All right, so what you're going to have here then is you're going to have one electron from the sp hybrid of bromine along with one electron of hydrogen. They will come to close to one another, overlap, and hybridize. Okay, so this here is an s orbital of hydrogen, as is this one over here. These represent the sp hybrid orbitals of beryllium, of a beryllium atom. And so now they overlap and form two covalent bonds, one on either side. Okay, so it's going to form a covalent bond. I got two on this side and two on this side. Okay, so it has the sharing of those electrons. So this is BeH2, okay, beryllium hydride is what has formed here. All right, is everybody good with that? I hope. All right, so very, very important to realize what's happening here. There's a promotion of one of the electrons from the full 2s orbital to an empty 2p orbital. Okay, those two come together and they blend or hybridize together. All right, and so this helps to explain why beryllium has a maximum of 4 electrons about it. Okay, so if this is my beryllium atom, now we see it's got 2, 4. That's the maximum number of electrons that beryllium can have around its valence shell. All right, so this is one example, and it helps to explain why hybridization takes place. All right, let's take a look at the next element on the periodic table, which is below carbon, and that is boron. All right, if we take a look at boron and think about its orbital diagram. So once again, let's quickly draw its orbital diagram. So it's got 1s, that's full with 2 electrons. Now we're going to go to the 2s orbital, which gives me 4 electrons. And then now I've drawn my 2p orbitals, and there's 1 for 5. So I've got 2, 4, 5 electrons for boron. So once again, this here represents the valence orbitals. Okay, they're the ones with the highest principal quantum number 2. Okay, these are my valence orbitals. Now, looking at this orbital diagram of boron, technically you would suspect or expect boron to have the capability of forming only one covalent bond because it only has one half-filled orbital. But this is not the case. No such molecule exists. So what happens instead, just like in beryllium, one of the electrons from the 2s orbital gets promoted to an empty p orbital. So once again, we see a promotion. Okay, we will promote an electron. And now we blend or hybridize these 3 orbitals together. And so now what has come together is an s orbital and 2 p orbitals. So we call this an sp2 hybrid. And once again, that empty p orbital is still there, it's just empty. Okay, so I have 3 half-filled p orbitals. Okay, and 1 unhybridized p orbital. Okay, so we'll label this so you remember that this is an unhybridized p orbital. Now, what's the shape of this particular molecule is trigonal planar. So if I take these 3 p orbitals, it is going to look like this, with 1 electron in each of these lobes. Okay, so this represents boron. It's trigonal planar in shape. And 120 degrees. Okay, so each one of these lobes, this one, and this one, are all called sp2 hybrids, each with one electron. Okay, so that's very, very important to note. So what can happen here is each of these half-filled orbitals can overlap with, say, a half-filled s orbital. So let's draw that quickly. Over here, I've sort of run out of space, and I'm going to overlap it with an s orbital of hydrogen. So what you're going to see here is there's going to be two electrons, one that came from the s, one of hydrogen, and one that came from the sp2 hybrids. And these form my three covalent bonds. Okay, so this is going to result in a covalent bond. This is going to result in a covalent bond, and this is going to result in a covalent bond. There is the overlap of the half-filled orbitals between a s orbital of hydrogen and an sp2 of boron. Okay, so that is very important to note what happens here. So when these atoms need to form covalent bonds, their orbitals blend or hybridize. All right, our last one that we're going to consider today is carbon, and this is going to help illustrate why carbon actually forms 4 covalent bonds. Once again, let's take a look at the orbital diagram. And so in this diagram here, we've illustrated only the valence orbitals. Okay, we didn't include the 1s because only the valence orbitals are important in bonding. Valence orbitals only. So once again, if you draw that, so don't forget, over here, I would have had a 1s orbital that was full. And we'll notice here, based on this diagram, orbital diagram, carbon should only be forming 2 bonds because it only has 2 half-filled orbitals. But we know that carbon has the capability of forming 4 covalent bonds. So once again, there is a promotion of 1 electron to the empty p orbital. And so what happens is now all 4 of these orbitals blend together to form an sp3 hybrid. Okay, and the sp3 hybrid has a very special shape, and you guessed it, it is called a tetrahedral. All right, so each one of these lobes has 1 electron that is now capable of overlapping with another half-filled orbital. Okay, so this shape is tetrahedral, and the angle of separation is 109.5 degrees. Okay, so once again, each one of these, if you were asked to label these hybrid orbitals, you would have to call it a sp3 hybrid. Just like you would have to call the one for boron sp2 hybrid, and for beryllium it's an sp hybrid. So you need to know the names of these hybrid orbitals, and you also need to know their shapes. Okay, how they are represented as their shapes. So this sort of just once again shows the diagram a little bit better as well. All right, so reminders that there is 1 electron in each one of these lobes. Okay, and so it has the ability to form 4 identical hybrid orbitals. Very, very crucial in our understanding of what hybridization is. So now what can happen is it can now covalently bond by overlapping with, for example, hydrogen atoms, the s orbitals, which are half full, to form CH4. Now, hybridization is only going to occur, this is very important concept to realize. These hybridizations only happen when bonds are going to form within a molecule, okay, not in an isolated atom. So if you were asked to draw the orbital diagram of a carbon atom, you would draw it as we have always in the past. But if it's involved in bonding, you then need to show how it hybridizes to form an sp3 hybrid. Okay, so this is a theoretical process which combines atomic orbitals to form new sets of orbitals that will take part in covalent bonding. And so sp3, if we take a look at this diagram at the very bottom, shows how the sp3 hybrid orbitals of carbon are involved in the bonds. Okay, we see the overlap taking place here. Okay, we got an overlap in each one of these. Okay, so what's happening is there is an overlap of the s orbital of a hydrogen atom with, and let's say, with a sp3 hybrid orbital of carbon atom. Okay, and so we have 4 of these. Okay, there's 4 overlaps. I've got one here, one here, one here, and one up at the top. Okay, so those are all overlapping to form my 4 covalent bonds. 4 covalent bonds. So 4 covalent bonds result. Okay, 4 covalent bonds are going to result here. All right, so I think I'm going to stop there because the next section sort of talks about our second problem, which is the formation of double and triple bonds. All right, so check the content page where you found this note and video. Your homework will be there for you to try. What I really encourage you to do is definitely read over this section so that you have a good understanding of how to illustrate and to represent and understand how these hybridization orbitals are formed. All right, so we'll see you in the next lesson.